Bismillahirrahmanirrahim. Assalamu alaikum students. Welcome to our 19th lecture of MTH108 Business Math 1. Today we will study about chapter 9, which is matrix algebra. Today we will start our new chapter. Let's see what are the objectives of the chapter. To provide an understanding of the nature of the matrix and matrix representation of data, provide an understanding of the algebra of matrices, and to provide applications of matrices and matrix algebra. So what we will cover mainly in this chapter, mainly we will see the introduction of matrices. We will also see some special types of matrices and the matrix operations. Then we will continue and we will see what do we mean by the determinant of a matrix. Using the definition of determinant, we will see what do we mean by the inverse of a matrix and how we can find it. And in the end of the chapter, we will see some applications of matrix algebra. So we start our today's lecture. Today we will cover mainly about the matrix, that is some introduction about the matrix and some basic facts. We will see some types of matrices and the matrix operations, which mainly include the addition and scalar multiplication in our today's lecture. And also we will see some properties of matrix operations. Okay. We start with the definition of matrix. You have already studied matrix in your college classes or earlier. What do we mean by a matrix? A matrix is nothing but a rectangular array of elements. What do we mean by the rectangular array? Okay, we say that when we are dealing with data, for example, we have some set of points, then what is our concern? What to do with the data? Our concern is mostly to organize the data in such a way that when we organize the data, it is meaningful, that it can be well shown, and it can be readily identified. For example, if we have some data, then we are mainly interested in organizing the data in such a way that whenever we look our data, we can easily get the information which represents our data. So basically we want to summarize our data, and the easiest way to summarize the given data is to write it in a tabular form. And whenever we want to write our data in tabular form, we use the matrix, because matrix best suits our requirements, because writing the data in tabular form or writing the data using the matrices satisfies our both the conditions. That is, by writing the data in the matrix form, we have organized it in such a way that it is meaningful and it can be readily identified. Let us take a very simple example by what do we mean by data and what do we mean by organizing the data in a way that it is meaningful and readily identified. For example, if you wish to maintain a record of test scores of 5 students, suppose we have 5 students and they have appeared in 3 exams, and we want to maintain this data, that is the number of marks these 5 students have obtained in these 3 exams, then we can maintain our data with the help of a matrix. How? Then for example, we have this as the test marks and this as the number of students. We have 3 tests, 1, 2 and 3, and we have 5 students. Let's say 1, 2, 3, 4, 5. Then what do we do basically is, for example, student 1 has obtained 81 marks in test 1, 72 marks in test 2 and 40 marks in test 3. Then we have collected this data, that whenever we look at our data, we can easily recognize that what do we mean by 81, what do we mean by 72, and the student has obtained 40 marks in test 3. Similarly, student number 2, let's say, has obtained 49 marks in test 1 50 marks in test 2 and 30 marks in test 3. Okay, this should come here and this should come here. Okay, now student 3, let's say, has obtained 60 marks in test 1, 48 marks in test 2 and 90 marks in test 3. Now student 4, let's say, has obtained 18 marks in test 1, 100 marks in test 2 and 45 marks in test 3. And student number 5, let's say, has obtained 80 marks in test 1, 44 marks in test 2 and 43 marks in test 3. Then we have 5 students which have appeared in 3 exams, and we have maintained a record of the number of students obtained the marks in each exam in a rectangular array form, in a tabular form. And by looking at this tabular form, or by looking at this matrix, actually, we can easily recognize, this matrix is easily readable, we can easily recognize that which student has obtained how many marks in which test. For example, student 4 has obtained 100 marks in test 2. If we are interested in knowing that how many marks student 4 has obtained in test 3, then student 4, which is 4th row, and the 3rd column, that is, this entry represents that student 4 has obtained 45 marks in test 3. Okay, so generally now we define matrix generally as a matrix containing elements Aij has the general form A is equals to A11, A12 and so on up to A1n, A21, A22 and so on up to A2n, and continuing this way AN1, AN2 up to ANn. Now this is the general form of representing a matrix, that is, A is the matrix and it contains elements Aij, where A with entries A11, A12 and so on up to ANn, or we can put it as here as AM, M, M and M. So this is the general form of a matrix. Okay, now what do we mean by these elements Aij? Now we look at some basic facts of our matrix which we already know, but we will simply revise them. Now the generalized form of the matrix which we have just written has m rows and n columns. We have to go back to a previous slide to look at how many rows this matrix has. Row 1, 2 and so on, continuing up to m rows, and how many columns? Column 1, column 2 and so on up to n columns. So this matrix has m rows and n columns. Okay, what further information we know about matrices? The entries of a matrix are called the elements indexed with double subscripts I and j. That is, the entries of the matrix are called the elements Aij. Aij are nothing but the elements of the matrix indexed with double subscripts. Here we have double subscript I and j. Now these subscripts have particular meaning. What does these subscripts mean? That they indicate the location of the element within the matrix. For example, A21. If I is equals to 2 and j is equals to 1, then the element will be A21, and the first subscript, that is 2, this represents the row position, that this element lies in second row, and the second subscript, that is 1, this represents the column position. That is, this A21 element lies on second row and first column. If we go back to our previous slide, which means that second row and first column. So this is the entry or element A21. So the general form of writing the elements Aij with double subscripts I and j has a particular meaning. What is the meaning? That the first subscript I denotes the row position and the second subscript j denotes the column position. For example, A21 is I is equals to 2 here, j is equals to 1 here. This implies this element A21 lies in second row and first column. How we represent our matrices? Matrices are usually written with uppercase letter and the elements are written with lowercase letters. Here we have seen in the general form that the matrix is represented by the uppercase letter A and the entries or the elements are represented by the lowercase letters A, I, J. And the entries are written inside either the parenthesis or the square brackets. We can also write our matrix A as equals to A11, A12 and so on up to A1n, A21, A22 up to A2n and continuing AM1, AM2 up to AMN. So we can use either of the brackets, either the square brackets or the parenthesis to represent our matrix. Up to now we have seen that how do we denote our matrix, how do we denote the entries of the matrix, and what type of brackets are allowed to enclose the entries of the matrix. Now we come to the important fact about matrix, which is the dimension or order of matrices. Now each matrix has some dimension called the order of the matrix, and this order or dimension basically denotes the number of rows and the number of columns of that matrix, and it is written as m cross n and read as m by n. For example, if we take our test score matrix again, then this is the test and this is the number of students. Then let's say we have 3 tests, 1, 2, 3, and we have 3 students A, B and C, and they have obtained some marks in different tests. 70, 80, 95, 40, 10 and 10. Okay, let us consider our student test example again. Then this matrix parenthesis, the round one or the square one. What will be the order of this matrix? This matrix has how many rows? 1, 2, 3, 3 rows. Okay. And how many columns? 1, 2, 3, 3 columns. So the order of the matrix is 3 by 3. And where we write the order of the matrix? On the right, on the bottom right of the matrix. That is on the right hand side of the bottom of the matrix. Here we write our order of the matrix if it is not clear. By practicing with the matrices, we will be familiar and we can easily recognize the order of the matrices, and we will not write these orders here because we will know them by just looking at the matrix. So order basically tells us that how many entries are to be enclosed within the brackets. If the order is 3 by 3, which means that the matrix will have 3 rows and 3 columns, and we will have 9 entries in total. One thing we have to observe, that the number of rows and number of columns can be any positive integer. That is, there is no condition that the number of rows is equals to number of n, or they should be only different. No. A matrix can have any number of rows and any number of columns greater than equals to 1. Okay. If we want to know that the element A22, what is the entry of the element A22 in this given matrix, let's say S, then how we can identify or how we can find the value of the particular element? Now, the first index I is 2 here, which means we have to look in the second row. The second index, the second subscript J is also 2 here, which means that we have to look in the second column. So this entry A22 is 80. Similarly, if we want to find the entry A12 in our matrix S, then A12 means the entry in the first row, that is first row, and second column, which is 40. Okay. If we are interested in knowing the entry A21, A21 means second row and first column, second row and first column, this is 70. One thing we have to keep in mind, that these index, the order of these subscripts cannot be interchanged. That is, the entry Aij is not equals to entry Aj, which we have clearly seen in our example, that entry A12 is different from entry A21. So by writing these entries or elements, we have to be extra careful by representing, by putting the values of I and J. If we will change their order, then we will be working with a different entry. Okay, so what will be the entry representing A41? A41 means we have to look in the fourth row and first column. First column we have, if we look at our matrix S, okay, but do we have any fourth row? No, we don't have any fourth row. So this entry does not exist in a matrix S of order 3 by 3 because there is no fourth row. So this entry basically does not exist. Okay. Similarly, if we want to find the entry A14, A14 means I is equals to 1, that is first row, okay, and J is equals to 4, which means first row, and J is equals to 4, which means fourth column. But we don't have any fourth column here, which means that this entry does not exist for a matrix of order 3 by 3. Okay, which means that the entries must have a maximum I and J equals to 3 and 3. That is Aij, where I can have maximum value between 1 and m, where m is the number of rows, and J can have the maximum value between 1 and n, where n is the number of columns of our matrix. So now we have seen that what do we mean by the order of a matrix, and given a matrix, we can, just by looking at it, we can easily see the order of the matrix and which entry Aij belongs to, represents which element. Okay. Now we look at some examples of our matrices and we will see their respective orders. For example, For example, if we have our matrix as 8 minus 8 5 3, then what will be the order of this matrix? The order is nothing but m cross n, where m is equals to number of rows and n is number of columns. Okay, so number of rows, we have only one row here, and how many columns we have? 1 2 3 and 4. So this matrix has order 1 by 4. Okay, second example, if we just write these entries in this way, then what will be the order of this matrix? First we have to write the number of rows. Here we have how many rows? 1 2 3 and 4 rows. Okay, and how many columns we have? Only one column. So this matrix has order 4 by 1, that is 4 rows and 1 column. Okay, let's look at one more example. We have our matrix 2 4 minus 6 and 5 by 2. What will be the order of this matrix? First we have to identify the number of rows. We have row 1 containing the entries 2 4 and row 2 containing the entries minus 6 and 5 by 2. So we have basically 2 rows, and the number of columns is 1 and 2. So this matrix has order 2 by 2. Okay, let's look at few more examples. We have our matrix 2 minus 5 10 20, 8 minus 5 10 and 20. What will be the order of this matrix? The number of rows we have how many? 2, and the number of columns we have 1 2 3 and 4. So this matrix has order 2 by 4. Now one more example about the order of matrix. Let's say we have a matrix with entries 3 3 3 6 6 6 9 9 and 9. Then what will be the order of this matrix? How many rows we have? 1 2 and 3. And how many columns we have? 1 2 and 3. So this is a matrix having order 3 by 3. So just by looking at the matrix, we can easily recognize the order of the matrix, and once we will get used to it, we will not write these orders on the bottom right side. These are just to understand the order, and later when we can recognize the orders immediately, we will not write these orders here. Now we come to some special types of matrices. First we have the row vectors, vector type matrices. Now vectors are special class of matrices. They are of two types, row vector and column vector. That is vector having only one row and vector having only one column respectively. Now what do we mean by a row vector? A row vector is a matrix having only one row, and the general form of the row vector denoted by R, because it is a row vector, so we will denote it by capital R, and the general form is R is equals to R11, R12, R13 and so on up to R1n. If we look at this vector or matrix, then this matrix has only one row and n columns. So this matrix has order 1 by n. So row vector, we call this vector as row vector. Why? Because it has only one row. Whenever m, this value of m is equals to 1, no matter what is the value of n, that vector or that matrix will be considered as row vector. That is, this matrix with elements Rij and dimension 1 by n, where R11, that is first row first column, is this entry, R12 is first row second column, and so on. For example, if we have a vector 1, 3, 5, then this is a row vector with only one row and how many columns? 3 columns. For example, if we write as 28, then is this a row vector? Yes, this is a row vector, because I have just said that the order m by n, whenever m is equals to 1, that vector or that matrix will be row vector automatically, no matter what is the value of n. So here we have one row and one column. So this is an example of row vector with only one entry, R11. Okay. Now, similar to the concept of row vector, we can also define the vectors which are vertical. Row vectors are horizontal vectors or horizontal matrices. What happens if the vector is vertical or if the matrix is vertical? Then these vectors are called as column vectors. So a column vector is a matrix having only one column, and the general form of the column vector, denoted by C because it is the column vector, so we generally denote it by capital C, and the general form is capital C written as C11, C21, and so on up to Cn or Cm1. Here I have used the square brackets to represent this column vector. Okay, now this column vector has, what is the order of the matrix? Generally m by n. And what is the order of this matrix? It has 1, 2, and so on m rows and only one column. So whenever this value of n is equals to 1, the resultant matrix will be the column matrix automatically, no matter what is the value of m. To define the column vector, we are only concerned in the value of n, that is the number of columns. And to define the row vector, we are only concerned in the value of m, that is the number of rows. So a column vector denoted by capital C is a matrix with elements Cij and dimension m cross 1 or m by 1. For example, if we have our matrix 4, 5, 10, then is this a column vector or is this a column matrix? Yes, this is a column matrix with only one column, but remember the number of columns we have to write after. So this, it has one column, and how many rows? 1, 2, 3. So this is a column matrix with order 3 by 1. Let us consider one more example. We have -3 and 10 by 3. This is again an example of a column matrix with one column. Okay, n is equals to 1 here, and how many rows? 2 rows. Okay, what about this example again, which we have discussed in our row vector? Now this has one column. Okay, we write 1 here, and this has only one row. So this is also an example of column vector or column matrix which has only one entry, C11. So now by looking at the matrices, we can easily identify that the given matrix is a column matrix or a row matrix. Now we come to some more classes or types of matrices. Next is a square matrix. A square matrix is a matrix having the same number of rows and columns, that is when m is equals to n. which means that the number of rows is same as number of columns. For example, if we have our matrix 5, 3, minus 1 by 3 and 4, then how many rows do we have? 2 rows. And how many columns? We have 2 columns. So this is an example of a square matrix of order 2 by 2. That is, the number of rows is same as number of columns, which means that m is equals to n here. For example, 28, is it a square matrix? Yes, of course, it is a column matrix, it is a row matrix, as well as it is a square matrix because it has 1 row and 1 column, satisfying the condition that m is equals to n. So this is a square matrix as well. Okay, one more example. 24 minus 5, 3 by 5, 48, 3 minus 1, 0. What is the order of this matrix? This matrix has basically how many rows? 3 rows. Okay, we write here as 3. And how many columns? 3 columns. So this matrix has order 3 by 3, which means that m is equals to n here, and the given matrix is also a square matrix. Now, once we have a square matrix, we also want to know, or sometimes we are interested in knowing, the diagonal elements. What do we mean by the diagonal elements? That is, these are those entries in the matrix which have the same subscripts I and j. That is, which lie on the diagonal with entries A11, A22, and so on up to ANN. For example, if we look at our first example of a square matrix, then what is A11 here? What are the diagonal elements here? We have 2 diagonal elements here. Now the diagonal elements will be equals to the value of m or n. We have m is equals to 2 here, so we will have 2 diagonal elements, which means that 2 diagonal elements A11, that is when I is equals to j, and A22, that is the element of second row and second column. So in example 1, we have A11 is equals to 5 and A22 is equals to 4. Okay, in example 2, the order is 1 by 1, which means that we will have only one diagonal element here, which is A11, which is 28. Okay, in example 3, the order is 3 by 3, which means that we will have at most 3 diagonal entries, namely A11, A22 and A33. And what are these entries? If we look at our matrix, A11 is the entry in first row, first column, which is 20. Okay, then A22 is the entry which lies on second row, second column, which is 40, and A33 is the entry which lies on third row and third column, which is 0. Okay. Now if we look at our third example, so basically these are our diagonal elements, A11, A22 and A33. In our first example, this is our diagonal with entries A11 is equals to 5 and A22 is equals to 4. Okay. Once we have a square matrix, that is the matrix having the number of rows equal number of columns, then in a square matrix we can easily identify our diagonal entries as well. That is the entries which have the same position of row and same position of column. Next type of matrix is the identity matrix. An identity matrix is again a special type of square matrix, that is a matrix having same number of rows and same number of columns, but with extra condition that identity matrix has only 1 as the diagonal entry and all other entries are 0. That is, if Eij denotes the elements of an identity matrix, then we are saying that what type of entries of this identity matrix are, it has 1 on the diagonal entries, that is 1 when I is equals to j, and otherwise 0, that is 0 whenever I is different from j. For example, if we have our matrix as 1 0 0 1, then first we have to recognize that is this a square matrix? Yes, it has 2 rows and 2 columns, so it is a 2 by 2 matrix. What are the diagonal entries? That is A11 and A22. Both are 1 here. Okay, then whenever I is equals to j, that is A11 is 1, when I is 2, A22 is 1. And what we have to do with the other entries? Whenever I is different from j, that is the entry A21, that is the entry A12 and the entry A21. These should be 0. So what we are saying actually is that an identity matrix is a square matrix having only 1 as the diagonal entry. So these are our diagonal entries A11 and A22, and they should have some particular value which is only 1, and all other entries should be 0, should have the values 0. Okay, for example, if we consider this matrix, this is a row matrix, a column matrix and a square matrix of order 1 by 1, and in this matrix we have only one diagonal entry A11 which is 1. So this is also an identity matrix, and we usually denote our identity matrix by capital I. We may write here 2 just to identify that what is the order of this identity matrix with subscript 1, that is, it is the identity matrix of order 1 by 1. Okay, if we have another matrix with entries 1 0 0 0 1 0 0 0 1, then this is a square matrix of order 3 by 3, and the diagonal entries, that is A11 is 1 here, A22 is 1 here, and A33 is also 1 here. So the diagonal entries are 1 and all other entries are 0. So this is an identity matrix of order 3 by 3. So identity matrix should be the square matrix first, and if we have the diagonal entries as 1 and all other entries as 0, then the matrix will be the identity matrix. Now one more type of matrix is a zero matrix. An m by n matrix whose entries are all 0 is called a zero matrix, and it is usually denoted by capital O. For example, if we have our matrix as 0 0 0 with entries all 0, then this is a matrix of order 2 by 3, that is, it has 2 rows and 3 columns, and the definition says that a zero matrix is a matrix having all entries 0. So all the entries are 0 here, and the zero matrix need not to be a square matrix. It may have any order. A zero matrix have no condition that m is equals to n. No, m and n may be equal or may be different. In the case of a square matrix, the zero matrix will be 0 0 0 0. So this is a square matrix of order 2 by 2. Now, up to now we have seen different types of matrices, what are their names, and the order of matrix. At times when we have a data, we want to rearrange our data to see the things from the different perspective. For this method, we use the transpose of a matrix. And what do we mean by the transpose of a matrix? That is the transpose of an m by n matrix A with elements Aij and denoted by A superscript capital T is an n by n matrix with elements Aij transpose equals to Aj. What are we doing in transpose of a matrix? In simple words, suppose we have a matrix A of order m by n. Here we also have to observe that we are not talking about square matrix only. The matrix may have any order m by n. That is, m and n can be equal, they can be different. Okay, we have a matrix A of some order m by n, and we want to take the transpose of the matrix. So the transpose of the matrix denoted by A with the superscript capital T is a matrix having order n by m. If we look at both the orders, what we have done, we have simply interchanged the number of rows with the number of columns. That is, by taking the transpose of a matrix, we interchange the rows with the columns of the matrix. For example, if we have our matrix A as 2, 4, -3, 8, 6, 10, then it is a matrix of order how many rows? 3 rows and 2 columns, and we are interested in taking the transpose of the matrix. So transpose of the matrix will have order 2 by 3, that is 2 rows and 3 columns. 2 rows means we will replace interchange the column by the row. That is, here the column will be the row of the matrix. That is, n will be now m. So first column is 2 minus 3, 6. This will become the row of the matrix. That is 2 minus 3, 6. And the second column will become the second row. That is 4, 8, 10. So the matrix obtained by interchanging the rows with the columns is a matrix of order 2 by 3, that is having 2 rows and 3 columns. And what do we mean by this notation? Aij transpose is Aj. For example, the first entry A11, so I is 1, j is 1, so this entry will stay as it is. Okay, by taking the transpose of the matrix, the diagonal elements will not change their position, they will stay as it is. That is, A11 is also at the same position in the transpose. The second diagonal element is A22. This is also at the same position, that is second row, second column. Okay, what about the entry A12? That is the entry at first row and second column, 4. Now this entry will be written in taking the transpose as second row. This will be the row and this will be the column. Second row and first column, that is A21. Now the entry A21 will be written as entry A12, that is first row and second column. The entry A31, that is the entry at third row and first column, will be written as the entry at first row but third column. A31 transpose. That is, we are interchanging the order of rows with the order of columns, and the matrix we obtained will have the order as n by m and the diagonal entries will stay at their position. Let us look at few more examples that how we can find the transpose of our matrix. Suppose we are given a matrix -3, 4, 8 and second row is 9, 3 by 2, 10. Then this is a matrix with 2 rows and 3 columns. We call this SB, and we are interested in finding the transpose of this matrix. Okay, then the transpose will have the order 3 rows and 2 columns. Okay, the first element will stay as it is. A12 will be A21 will be on A21 position. A13 will be on A31 position. Okay, A21 will be on A12 position. A22 will stay as it is, and A23 will be on A32 position. So we will switch the order of I and J, and we will obtain the transpose of our matrix. That is what is happening here. A12 is, after taking the transpose, shifts to A21. A13 shifts to A31. A21 is shifting to A12, and A23 is shifting to A32. Okay, one more example. Suppose we have a matrix C is equals to 10. Okay, this matrix have order 1 by 1 with only one entry C11. So what will be the transpose of this matrix? The transpose of this matrix will be the same, that is C. Okay, one more example. What is the transpose of the matrix O, which is the 0 matrix? Let's say we have our matrix O as 0, 0, 0 and 0, that is a 0 matrix with order 2 rows and 3 columns. Then the transpose of this matrix will be a 0 matrix again, but with the different order, that is with the order 3 rows and 2 columns. So the transpose of this matrix in this case will be a 0 matrix but with different order. This is our 0 matrix. The transpose is again a 0 matrix, but the order is changed. Now we are interested in some more examples of a transpose of a matrix. Suppose we have our matrix D as 4, 6, 8, -2, 10, 0, 40, -1, -2. Now this is a matrix of order 3 by 3, that is 3 rows and 3 columns. The transpose of this matrix, since this is a square matrix, so the transpose will have the same order as the original matrix, that is 3 by 3, but the entries will be interchanged. The first one will remain as it is. A12 will be A21, A13 will be A31, A21 will be A12, the diagonal entry A22 will remain as it is, and A23 will be A32. Now the entry A31 will be A13, A32 will be A23, and the diagonal entry A33 will stay as it is. So in case of square matrices, the transpose will have the same order, but the entries will be shifted to Aij will be shifted to Aj. That is, what are we doing? Aij is shifted to Aj. For example, we have our, let's say, identity matrix of order 3, which is 1 0 0 0 1 0 0 0 1. Then this is the identity matrix of order 3 by 3. The transpose of this matrix will be again the square matrix of the same order, 3 by 3, and we have observed that the diagonal entries stay as it is and the other entries will interchange, means this will interchange with this one, this will interchange with this one, and this entry will interchange with this one. Since all other entries are 0, which means that the transpose of the identity matrix is the same matrix and of same order. Now after this information, that is the definition of matrix by order of matrix and their special types of matrices, we have some practice questions from section 9.2. And now we look at one example, that is, we are given the formula of the entries of our matrix and we are asked to find that particular matrix representing the formula. For example, we are asked to find a 2 by 4 matrix A, for which the formula for the entries is given as Aij is I plus j whenever I and j are same, that is the diagonal entries, and 0 otherwise. If we are given a formula about the entries of a matrix and we are also given the order, then with the help of these two information we can formulate our required matrix. So the required matrix should be of order 2 by 4, that is 2 rows and 4 columns, that is A11, A12, A13, A14, A21, A22, A23, A24. Now we have to find these entries A11, A12 and these all 8 entries. Now A11 will be I is equals to j, so we will obtain 1 plus 1, which is 2. A12, since I is different from j, this will be 0. This is the same with A13 because I is different from j, and the same with A14. Now A21 will be 0 again because I is different from j, that element will be, that entry will be 0. This is the same with A23 and A24, and the entry A22, since I is equals to j, the entry will be I plus j, that is 2 plus 2, which is 4. So our required matrix A is 2 0 0 0 0 4 0 0, the matrix of required order 2 by 4, where the entries satisfy this formula. Now what will be the transpose of this matrix? The transpose of this matrix will be the matrix of order 4 by 2, that is 4 rows and 2 columns, and the first column will become first row 2 0, the second column will become second row, that is 0 4, the third column will be the third row and the fourth column will be the fourth row. So this is the transpose of this matrix of order 4 by 2. Now we have seen the special types of matrices, how we can recognize the order of the matrix, and what do we mean by the transpose of a matrix. Using these information, now we come to the matrix operations. Today we will only discuss about the addition and the scalar multiplication of matrices. We have done this matrix operations many times, but now we will study them in a slight detail, and just for the sake of revision. Now there are several occasions when data stored in a matrix needs to be manipulated. For example, a teacher may want to know the class average on a given test or a student average for the 3 tests. That is, we have a data and we want to do something with the data. That is, we want to add or subtract or find something more. Now, matrix operations allow for manipulating data and for performing computations while keeping the data in the matrix form. And these operations are of 3 types. Matrix addition. Once we will define the addition, we can also define the matrix subtraction, scalar multiplication, and the matrix multiplication. We start with our first operation, that is matrix addition and subtraction. Now 2 matrices may be added or subtracted if and only if they have the same dimension or they have the same order. For example, we have 2 matrices A and B, both having the order m by n. Then the new matrix C will have the same dimension as the matrices A and B, and the new matrix C will be found by adding the respective elements of A and B. That is, the matrix C having entries Cij will be nothing but adding the respective entries of A with the respective entries of B. And for this reason, we need the same order of the matrices to be added together. And for all I and j. Now, if a matrix B is required to be subtracted from the matrix A, then the new matrix C will be Cij and written as Aij plus minus 1 into Bij for all I and j. Now we look with the help of examples that what do we mean by this Aij plus Bij for all I and j. And we will see the matrix subtraction a bit later. For example, we have a matrix A as 4 minus 10, 5, 8 by 3, and we have our matrix B as 3, 4, 14 and 0. We have 2 matrices of order 2 by 2 and 2 by 2. Both the matrices have same order, so these matrices can be added together to form a new matrix. That is, the matrix C can be formed by adding the matrix A and B, because both the matrix A and B have the same order. And how? By adding the respective entries. That is, the respective entry A11 will be added to the entry B11. Okay. We have also seen in our previous slide that the new matrix C obtained by adding the matrices A and B will have the same order as of matrix A and B. So this matrix C will have the order 2 by 2. What will be the entry C11? Now this will have entry C11, C12, C21 and C22. C11 is nothing but adding the entries A11 with the respective entries of the matrix B, B11. C12 will be adding A12 with the respective entry B12. C21 is nothing but adding the respective entries, 2-1 entries of the matrices A and B, and C22 will be adding the entry A22 to the entry B22. So this matrix C will be equals to C11 is A11 plus B11, which is 4 plus 3 minus 10 plus 4, 5 plus 14 and 8 by 3 plus 0. And the new matrix obtained by adding the 2 matrices is 7 minus 6, 20 and 8 by 3. 19 and 8 by 3, 14 plus 5 is 19. Okay, what will be the transpose of this matrix? The transpose of this matrix will be the matrix of order 2 by 2 with the diagonal entries as it is and these other entries interchange. That is, here we will have 19 and here we will have -6. Okay. Now we want to see what do we mean by the scalar multiplication of a matrix. A scalar is a real number, and so far the matrices we have seen have entries as real numbers, but the matrix may have entries real or complex. There is no restriction, but we are restricting ourselves only to the real entries. Okay, so scalar multiplication of a matrix is the multiplication of a matrix by a scalar, that is multiplying the scalar to all the entries of a matrix. Generally speaking, if K is a scalar and A is our m by n matrix, then the scalar multiplication, if A is our matrix of order m by n, that is A11, A12 up to A1n, A21, A22 up to A2n, and so on up to AM1, AM2 up to AMN. If this is our matrix A of order m by n and K is our scalar, then the scalar multiplication will be nothing but multiplying this scalar with each entry of the matrix, that is multiplying the scalar with the entry A11, A12 and so on. Similarly, K A21, K A22 up to K A2n, and continuing in this way A M1, K A M2 up to K A Mn. So what do we mean by the scalar multiplication of a matrix? That is, we have a scalar, a real entry, may be positive, negative or 0, and we multiply this scalar with our matrix, that is, we multiply this scalar with each entry of the matrix. For example, we have our matrix A as 2, 4, 6, 8, 10, 12, and our scalar K is, let's say, 5. Then our scalar 5A, which is Ka, where we know the value of K here, is nothing but multiplying the scalar with each entry, that is 5 into 2, 5 into 4, 5 into 6, into 8, into 10 and into 12, and we obtain our matrix with these entries as just the scalar multiple of our given matrix. That is, we have multiplied our scalar with each entry of the matrix. Now, using the scalar multiplication, we now define the matrix subtraction. How? We were given with two matrices A and B, and the matrix subtraction in this case is defined as C, having the entries C, I, J. If we are asked to subtract matrix B from A, this will be A, I, J plus -1 into B, I, J for all I and J. So what we are doing basically in our matrix subtraction, our matrix Aij stays as it is. We are taking the scalar multiple of our matrix Bij, that is, we are multiplying the matrix Bij with the k is equals to -1, and then we are adding the resultant two matrices, that is the matrix Aij and the scalar multiple of the matrix Bij with k is equals to -1. So by using the matrix subtraction, we have done it many times, but we have never looked into the detail that by using the matrix subtraction, in fact we are using the scalar multiplication. That is, the matrix we want to subtract is first multiplied by the scalar -1 and then added to the first matrix A. Let us see with the help of examples what do we mean by the scalar multiplication and the matrix subtraction. For example, we are given with the matrix A is equals to 4, -10, 5 and 8 by 3, and the matrix B as 3, 4, 14 and 0. And we want to find our matrix D, which is nothing but the difference of B to A. Then in this case, first we have to multiply our matrix B by the scalar -1, which is -3, 4, -14 and 0. Okay, and now we will add our matrix, we will add the resultant matrix to B with the minus, which is 4, -10, 5, 8 by 3, and adding the scalar multiple of matrix B with scalar as -1. What do we get? Now solving the, we are doing the same procedure of addition, that is adding the respective entries. This should be -4 here. Okay, and so this should be minus. Now we have 5 -14 and 8 by 3 plus 0, and we obtain 1, -14, -9 and 8 by 3. So this is the matrix we have obtained by subtracting B from matrix A. How? We have taken the scalar multiple of the matrix B first with the scalar k is equals to -1, and then we have added the resultant matrix to our matrix A. Okay, now let's consider one more example. We have a matrix S given as 1, 2, 3, and a matrix T given as 1 by 3, 2 by 3 and 1, and we are interested in finding T minus S. Okay, first we will write the matrices 1 by 3, 2 by 3, 1, -1, 2, 3, which means that we can remove this step, that is multiplying the matrix S with the scalar k is equals to -1, and we can solve them directly as well, that is adding the respective entries, which is 1 by 3 -1, 2 by 3 -2 and 1 -3, and we obtained as -2 by 3, -4 by 3 and -2. So T minus S is a matrix with all the entries negative, and since we have said that a matrix may have a real entry or a complex entry, so having negative entries is not a problem. And here both the matrices S and T have the same order, that is 1 row and 3 columns, both are row matrices, so they can be added or subtracted easily. Now we come to some properties of our matrix operations, that is the properties of addition, scalar multiplication and transpose. Our first property is that the transpose of our 0 matrix is 0 again. We have seen it already. Our second property is that the transpose of our identity matrix is our identity matrix again. We have also seen this when we were looking at the examples of transpose. Third property is we have a matrix A with a transpose, and we take the transpose of it again. What would be the guess that what is the answer of this triple transpose? The answer is simply our given matrix A. That is, the double transpose of a matrix is nothing but the original matrix. Okay, now if we have two matrices A and B and we want to add them, then we can add them in any order we want. That is, A plus B is same as B plus A. Mathematically, we say that this is the commutative property of addition. That is, they commute with respect to the addition. No matter in which order we want to add them, we can add them and obtain the same result. Okay, if we have three matrices A, B and C and we want to add them, then the matrices can be regrouped and added and we obtain the same result. That is, on the left hand side, if we add our two matrices B and C and then add the resultant to the matrix A, is same as if we add our matrices A and B and then add the resultant to the matrix C, which means that by adding matrices we can regroup them and add them and we obtain the same result. Our sixth property is, if we add the zero matrix to our given matrix A, we obtain our original matrix A, which means that zero matrix in this case acts like the identity 0, acts like the addition identity 0 for the case of real numbers. That is, zero matrix is nothing but the identity with respect to the addition, identity with respect to the addition of matrices, and it acts like the number 0 in real line. We have some more properties of our matrix operations. Our seventh property says that if we have two matrices A and B and a scalar k, then either we add the two matrices and multiply with the scalar, or we multiply with the scalar and then add them, we obtain the same result. That is, scalar of the addition is same as addition of the scalar multiple, or the scalar of the sum is same as sum of the scalars. Okay, if we have two scalars k1 and k2 and a matrix A, then either we add the two scalars first and multiply with our matrix A, or we separately take the scalars and add our matrix, add them, we obtain the same result. For example, if we have two scalars, in the case of seventh property, for example, if we have our scalar k is equals to 5, then 5 multiplied by the addition A plus B is same as the scalar multiple of A plus the scalar multiple of B. In the case of property 8, for example, we have two scalars 3 and 5, then either we add them and take the scalar multiple, or we take the scalar multiples separately and add them, is this same. Okay, now again ninth property says that if we have two scalars k1 and k2 and now the scalar multiples, in the eighth property two scalars are added, in the ninth property two scalars are multiplied. So if we take the scalar with respect to scalar multiple with respect to k2 and then respect to k1, or we simplify the scalars and then take the scalar multiple of A, or if we take the scalar multiple of k1 and then with the k2, they are all the same. That is, by taking the scalar multiples, when we have more than one scalar multiples, the order does not matter. For example, if we have two scalars 3 and 5 is same as 3 into 5a, which is same as 5 into 3a, which is nothing but 15a. Why we have these properties? Because the scalars are real numbers, and real numbers satisfy these properties actually. Our 10th property is that a scalar multiple of a matrix with a zero matrix, that is when k is equals to 0, is nothing but a zero matrix. And the 11th property says that a scalar multiple of a zero matrix is again a zero matrix. We have few more properties of matrix algebra. These properties are very well known and we use them in our daily life, but we never recognize them. Our 12th property is that minus a is nothing but the scalar multiple of our matrix A with the scalar minus 1. We have just seen it when we were trying to solve with the matrix subtraction. If we have our two matrices A and B and we want to take their transpose, then this is nothing but the sum of the respective transpose. That is, transpose of the sum is same as sum of the transpose. We have 14th property as the transpose with the scalar multiple, that is, we have a matrix A with a scalar multiple k and we are taking the transpose. This is same as k into the transpose. That is, either we take the transpose first and then take the scalar multiple, or take the scalar multiple first and then the transpose. They are the same. For example, if our k is equals to 3 and our matrix A is a row matrix 1, 2, 3, then Ka will be equals to 3, 6, 9, and the transpose, first we are solving the left hand side. The transpose will be a column matrix 3, 6, 3, 6, 9, and now the right hand side. First we will take the transpose of our matrix. This will be a column vector 1, 2, 3, and multiplying the scalar with the transpose, which is 3 multiplied with the column vector, and we obtain the same answer. So now we have seen some properties of our matrix algebra, which include the addition and the scalar multiplication and the transpose and subtraction. We use these properties very often, but now we have collected all the properties related to the matrix operations of addition, subtraction, scalar multiplication and transpose. So with these properties we end our today's lecture. What we have studied today, we have studied about the matrices, why we need them and their proper definition, along with some examples of matrices. We have also studied the basic facts of matrices, which includes the notation, what do we mean by the elements of the matrices, dimension, and some examples to look at the dimension of the matrix. Then we have studied the special types of matrices, which mainly include the row matrix, zero matrix, square matrix, identity matrix, and the diagonal matrix with diagonal entries. Then the next thing we have studied was about the transpose of a matrix and how we can take the transpose of a matrix. Then we have seen that what do we mean by adding two matrices, subtracting two matrices, and taking the scalar multiple of a matrix, and what are their basic properties. With this we end our today's lecture. In our next lecture we will study about the matrix operation, which is the matrix multiplication, and some equations representing the matrix. See you in the next lecture. Allah Hafiz, students.